Hi everyone, and welcome to video number 3 of this series. So last time we were talking about the probability current J in a superconductor and the formalism. Until now, what we had done is we had assumed that there is no electromagnetic field present. Now next, what I'm going to do is I'm going to introduce an electromagnetic field. So we are going to assume that there's a magnetic field present as well. And what happens in the presence of an electromagnetic field is the momentum operator, it gets modified. So in the absence of a field, the momentum operator is now in the presence of an electromagnetic field, our momentum operator gets modified and it becomes now here the vector A is the vector potential of the magnetic field. And if you're wondering how this expression comes about, then I'm not going to go into the details of the derivation as it is quite involved. Also here, uh, Q is actually the charge of the Cooper pair, which will be minus 2e because there are two electrons in the Cooper pair. And so the probability current, the expression for the probability current is now modified as. Now, I want you to recall from before what we had said about rho and psi. So I want you to recall that rho is nothing but psi star times psi. So we can actually write psi as the under root of rho times some phase factor, which we don't know. And actually, rho is positive because this is just the norm of psi, the square of the norm of psi. So we know that rho is positive. So we know that this is a valid way of writing psi. And here, theta is a function of both space and time. And I'm going to actually write the gradient of psi here because we are going to we'll need the expression later. And so if we again consider the expression of the probability current, this operator actually acts on psi, and we already have written the expression of the operator acting on psi. So we can just take the real part uh, of uh, of this thing, and I'm going to write it down now. So the right hand side comes after we have taken the real part of this expression. Now we are going to call this quantity, which we have in the brackets here. This is something known as the gauge invariant phase gradient. And so we can rewrite uh, the expression of the probability current now in a more compact way. So we can write it as h bar rho over m times gamma. Now we are going to make an additional assumption here. And the assumption is that the state psi can be taken to be a stationary state. That is, rho is constant with time. Note that rho can change with space inside the superconductor, but it will not change with time. So what we are actually talking about is a steady state. So in a steady state, a quantity does not change with time, but it can change with space. That is, it can change within, uh, it can change with the spatial coordinates. So I'm going to state the assumption here, and you can actually refer to chapter 21 um, of Feynman's book, which I mentioned in the previous video, for why this assumption holds. Now, next, we are going to define a new quantity and we'll denote it with the uppercase lambda. We will call this quantity as the London coefficient. And we will next define another quantity which we will call the supercurrent. And we will denote it with J with a subscript S. We will define it to be Q times J. And again, to remind you, Q is minus 2 times E, which is the charge of a Cooper pair. Next, I want you to consider the quantity that is the London coefficient times the supercurrent. Now, simplifying it, we get this. Now, if we apply a curl to both sides of this equation, uh, we will get something remarkable, and I'm just going to show what exactly is that. So let's just apply uh, curl to both sides of the equation. Now, to recall from Maxwell's equations. So first of all, the curl of a gradient is always zero. This is a very well-known fact. And the second thing is, which we get from Maxwell's equation, is the curl of the vector potential A equals the magnetic field. So we can rewrite this equation as the magnetic field equals the negative of this quantity. Now this equation has another very popular name. This is known as the London equation. Now further, I'm going to use the Maxwell's equations. So the curl of the magnetic field can be written as this. I'm going to assume that the displacement current is zero. So this term actually goes to zero. And Gs is the current density. So further, if I take the curl of this quantity, now I'm going to simplify the left-hand side. So this actually becomes the gradient of the divergence of the magnetic field minus the so-called Laplacian of the magnetic field. And the right-hand side from this London equation expression, which we have above, we can actually write this as minus the magnetic field over the London coefficient, that is this uppercase lambda. And so the divergence of a magnetic field is known to be zero. So I can actually write this equation as the Laplacian of the magnetic field equals this. Now this is a remarkable equation. And this equation actually states that this quantity is proportional to the magnetic field inside a superconductor. So what we can say something very significant from this. Now we can say something very significant by looking at this equation, and this is that there can be no non-zero homogeneous magnetic field that can exist in a superconductor. That is, there cannot be a uniform field inside a superconductor. If there were a uniform magnetic field, it would have to be zero. And this is a very famous result, and this is actually known as the Meissner effect. And the Meissner effect actually leads to perfect diamagnetism of superconducting materials. And for this, I would point you to the reference that is chapter 12 on superconductivity in the textbook Introduction to Solid State Physics by Charles Kittel. That is all for this video. I'll see you guys in the next video.